In this video, I am going to talk about what is regularization in machine learning. We'll take an example. So here is the least square cost function. So we're trying to minimize the cost functions like this. We have target variable as y and x as the list of independent variables or features. We have got the parameters, the beta naught and beta 1. And if you have more features, then you will have more number of parameters. So how do we find out the values of the parameters? Well, we optimize this cost function, and then that's how we find out the beta parameters, right? And the algorithms that we can use could be the ordinary least square, the gradient descent, or the maximum likelihood estimation, right? So with several such algorithms, we can find out the values of betas, right, which are the weights, or we can also say that these are the parameters of a model. The problem that happens, or the issue that we often face, is that we always optimize the cost function on the training data. So if you have some familiarity with model building using machine learning, you know that when you build a model, you actually divide the sample into two groups. One is training data. So this is your training data. So you build a model in training data and do the testing or validation in test data. This is also known as the holdout sample data, right? So you do not show this section of data or the holdout data or test data to your model or to the optimization algorithm. Okay, so that causes a problem known as overfitting. So the model will fit well on training data, but it may not fit well on the test data. So which will mean that any given new data you use for model output, it's not going to be very efficient, or it's not going to be very useful. So the issue of overfitting is something that we often come across because the model is always good on training data in most times, but not so good on test data. So how do we ensure that even while we do the optimization, this is taken care of? So this is taken care of by a technique known as regularization. Okay, so it helps overcoming the overfitting issue. So if there is overfitting issue in your model, or there is a possibility of overfitting issues in the model, then with regularization one can overcome this issue to a large extent. So why do we call this as regularization? We call this as regularization as it helps keeping the parameters regular or very normal. Okay, and we'll understand what regular and normal means when we say that the parameters have to be regular and normals. Okay, so what is regularization is all about? Okay, so a few points to understand on regularizations. So generally we do not want huge weights in our model. Okay, so if a model is something like this, we do not want beta naught, beta 1 or beta 2 to be a huge number. This weight should not be very high. That's not expected in a model. The reason behind it, the reason is that if beta naught, beta 1 or beta 2, these weights are very large, then even a small change in the weight, can potentially make large difference in the target variable, right? Because if this is large, right, a very small change in the beta will have a very large impact on the target variable y. Remember, if you take the first differentiation, the first derivative, you actually get beta 1, right? The rate of change of y with respect to x is nothing but your beta 1. And if beta 1 is large, then it's going to be very sensitive. A very small change could bring about a lot of changes in the value of y, and that's not something we expect, because we want y to be more robust, or more robust to any change to the parameters, right? All right. And if that is the case, then it's less likely to be overfitting case, because what happens is that when you use new data for fitting your model or even evaluating your model, a lot of times the beta that your training data has will not be the same in a new data, right? And that makes a lot of difference to the y. Okay, and that's why we do not get a good prediction on test data or new data when the model itself has overfitted. So given this intuition, and given the fact that we have now understood why do we not want higher weights, we can have something that actually manages this, or something that can make sure that the weight is smaller. So essentially what regularization does is it puts zero weights to the features, to the the variables or the features that are not very important. Okay. Secondly, and there's not too much of weight on any feature, like not a single feature in the model should get very high, extremely high weight, because that becomes a very important variable, and it could cause problem, because any change in the new data could bring disaster to the model if one or a very few variables or features are so important. So so the two things which are important: smaller weights, and secondly, if some feature is not very important, then have zero weight. Okay, and then none of the weight, or none of the weights of the features should be very high. So that should not be the case. So the three things that regularization ensures it's present in the model, and as a result of which we will be able to overcome the problem of overfitting. So that's the idea behind regularization. Now let's learn a bit of mathematics. Okay, how do we how does regularization handle this problem? How does able to overcome this? Now we have this least square function in place. Now that's a cost function. Well, in the optimization, in a simple optimization, we go on to minimize the least square function, which is a cost function in this case. When we add the regularization, we actually add another term to the optimization function. Okay, so I'll just pronounce it for you, and then I'll of course explain. This is lambda by 2 multiplied to sum of this is the modulus of betas. Betas is exactly same. These are the weights or the parameters, and then this is to the power p, where p can be 1 or 2. Sometimes it would be 1, and sometimes it could be 2, and many times it could also be more than that. And it's still a convex optimization problem, so the same algorithms that we had used can also be used most of the times. Sometimes there will not be a solution, but there will be cases where you won't get a a very rather straightforward solution, but most of the times you will get. Okay. So here is the new cost function. Okay, I've just written it just to make sure that it is understandable. So we actually take the summation of the error square, right? So that's our least square. We have added this term, and this term is known as the regularized terms. Okay, we have lambda, which controls for how much this beta parameter should be low and at the lower end, or should be reduced. And this is the summation of the modulus of betas. Okay, and it is raised to the power p. P could be 1, p could be 2. It could be different than 1 or 2 also, but the two popular ones are the 1 and 2. Okay. Now this ensures that we not only minimize the square of the error, we also minimize the sum of the weight, so that the weight is also controlled. It is not very high for any particular feature, and for any feature which is not so important, we can have a zero weight. So in that case, a feature selection itself is taken care of when we use regularization. So it's not just helps in overcoming the overfitting problem, it also helps in selecting the feature, because a feature for which the weight is 0 is as good as not using that feature in the model, right? So that's also another advantage of using regularization. There are basically two types of regularization, and I've already said what could be the values of p1 and 2, right? And based on based on what the values of p are, and based on whether we are using a modulus or not, we define the L1 and L2 regularization. So before we understand what L1 and L2 are, we'll try to understand in terms of a loss function, L1 loss function and L2 loss function, and then it becomes easier to understand L1 regularization and L2 regularization. In L1 loss function, so loss function is nothing but your difference between your target variable and then what you actually get from the your model, right? So this is what we get from the model, and this is the target variable given. When we take the difference, we actually get the error term, and when you take a summation of that, summation of yi minus f of x, right? When you take the modulus of that, we call that as L1 loss function. We can also call this as least absolute regression, right? So yeah, so this is the modulus. On the other hand, we can also take the square, right, which is more popular. Least square itself is more popular than the modulus one, right? So instead of a modulus, we have just taken square of that. So what happens is modulus is that the error terms becomes positive. All the error terms they tend to become positive, and then when you do the summation, and there is no issue. Otherwise, they will cancel out, and it will tend to be 0. Whereas here we are squaring the error terms before adding them up. Okay, so it is just the difference in which we are making all the errors positive, right? The first one we're calling it as L1 loss function. The second one we're calling it L2 loss function. So this is L2 loss function where you have a least square case. We are summing this square of the error. Where this is in the first case we are taking the modulus of the error and then summing. So that's L1 loss function. So this is the difference between the formulation of loss function. Regularization L1 and L2 regularization both are of similar type. Okay. One thing to remember here is that in the first case we can have multiple solutions. We can have that. Whereas in the second case where we have a least square, we always have a single solution. Okay. So we have a closed form solution in this case, where in the first case we may not have a closed form solution. The first one we also call that as a lasso regression, okay, and the second one we call that as a ridge regression. We'll see a bit of it. Okay, so how do we relate this to regularized terms? Now we have learned about the L1 and L2 loss functions, right? But what is L1 L2 regularization? So here is what L1 L2 regulations are. In the L1 regulation, we have come across this regular addition of regularized term to the least square. Now this is the least square, right? This is the least square regression cost function. We have added this one, which is a regularized term, to this. Now if the regularized term is summation of the modulus of the betas or the modulus of the weights, is just the W has been used instead of betas as the weights. Okay, so that we call that as L1 regularization. On the other hand, if we are summing, or we are taking the sum of the these squared sum of the square of the beta parameters, then we calling that as L2 regularization. It's pretty similar to what we have seen for the L1 L2 loss functions. If you're taking modulus, it is L1. If you're taking square of that, it is we essentially calling it as L2 regularization. Okay. So this section we call that as a lasso, and this we call it as a ridge. Okay. So this is simply additional names to so depending on what you use, you actually call by the name. Okay. Alright, so what are the uses? I've already said about it that we actually use lasso and ridge to overcome overfitting. Secondly, to select the best possible set of features for a model, so that the prediction accuracy is quite good. So that's the intention of using L1 and L2 regularization. So finding optimal weights is a challenge, right? So what is the optimal weight by using L1 and L2? Okay, so that is the biggest challenge. Okay, so there are several ways, several techniques in which one can get to find the optimal weights. I'm not going to talk about it. We'll see that in an example in one of the next videos, where I'll take a data and showcase you L1 and L2 regularization, and see how we can optimally find out the best set of optimal weights. How we can tune the weights, how we can find it out a suitable set of weights which will be very good for prediction. Prediction accuracy is supposedly supposed to be improved once you use L1 and L2, and whether to go for L1 or L2 will also depend on quite a number of things. Sometimes L1 will do better than L2, sometimes in other way around. There's no science behind it, but there's always good to try both and then see which one is working better, or better on your test data. So we'll see one example to understand what we have learned, the theory that we have learned so far, and that will be better and more clearer. Thank you so much.